In Chapter 11, we're going to start talking about sequences in series. A sequence is a list of numbers written in a definite order, and the sequences that we are looking at are infinite sequences. So here we have sequence denoted with the squiggly brackets a sub n, and here our n starts at 1 and goes to infinity. So n is kind of like the index of our sequence. So here's an example written out explicitly. We have 1/2, 2/3, 3/4, and so on. So what we want to do is we want to look at a general formula for this sequence. So a sub n, it looks like the numerator is incrementing by ones, 1, 2, 3. The denominator is also incrementing by ones, 1, 2, 3. And so what we have is n over n plus 1 with a starting value of 1. So if n is 1 here, 1 over 1 plus 1, that's 1/2. And n is 2, 2 over 2 plus 1, that's 2/3, and so on. That works. So now we're going to do it again, and we want to try to determine what the a sub nth term of the sequence is. That is, we need to find a pattern for this sequence. So a couple things to pay attention to. First thing that I notice is 3, 4, 5, 6, 7. And if we want to start at n equals 1, then it looks like the top should be n plus 2. Okay, starting at n equals 1. Let me do this. Next thing I notice is the denominator looks like powers. That looks like 5 to the first, 5 to the second, 5 to the third, 5 to the fourth, 5 to the fifth. So it looks like 5 to the nth power. And then the next thing you notice is the signs here. We are alternating from positive to negative to positive to negative, positive. So to do that, we'll do a -1 to the nth power. Does that work? No, not exactly, because if n is 1, then this would be -1 to the first. That would give me a negative number. How about now? Now if I have -1 raised to the n plus 1 power, now it works out, and the sign's alternating. Top is incrementing by ones, and the denominator is powers of 5. Next, we want to look at what it means to have a limit of a sequence. So the sequence a sub n has a limit L, and we write the limit of a sub n as n approaches infinity is equal to L, or the a sub n term is approaching L as n approaches infinity. And that is, we can make the a sub n terms as close as we'd like to L by taking n to be sufficiently large. And if the limit exists, we say it converges or is convergent. Otherwise, the sequence diverges or is divergent. So, this kind of reminds you of limits of functions, except what we have is instead of having a function, what we have is like a set of points, because the values that n takes are integer values. So here we might have this set of dots, and this is n equals 1, n equals 2, n equals 3, n equals 4, and so on. And here it would look like this would be our L, whatever that is. And this looks like a convergent sequence. So how do we actually calculate these limits? How do we evaluate these limits? Well, we've got this theorem, Theorem 3, that if the function f of x has the limit L, and if f of n is equal to a sub n, where n is an integer, then the sequence has a limit L. So here what we're doing is we're saying, hey, we've got this function which passes through all of the points of our sequence. So that's a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and so on. So if the function, which passes through all the points of our sequence, has a limit, then the sequence also has a limit. And we have a lot of rules for dealing with limits of functions from Calc 1. Suppose we could do an example. The limit of the sequence 1 over 2 to the n. So we don't know what this limit is, but we do know if I use this function 1 over 2 to the x, the values of x equals 1, x equals 2, x equals 3, and so on, give me the values of my sequence. And I know that this limit approaches 0, so I know that this also approaches 0.